Hello everyone, welcome to the lecture of nMOS inverter. In the previous lecture we have seen alternative pull-ups. In that nMOS transistor is using as a load, and in that depletion and enhancement transistors are using as a load. In that nMOS depletion transistor is better when compared to the enhancement mode transistor as a device. So we are going to see inverter of nMOS with nMOS depletion mode transistor as the load device. Hello everyone, welcome to the lecture of nMOS inverter. In the previous lectures we have seen nMOS transistor operation, then its characteristics and its use as pass transistor. Then with that circuit we have seen as nMOS inverter with different alternative pull-ups. In that we have concluded that among the nMOS inverters with two nMOS depletion and nMOS enhancement loads, nMOS depletion is better. Therefore, we are seeing in detail of that nMOS inverter with nMOS depletion mode transistor as the load device. In this lecture, you are going to learn the nMOS inverter operation and characteristics. The contents of this lecture are nMOS inverter, its operation, its transfer characteristics and its sizing. See the nMOS inverter construction first. nMOS inverter construction. This nMOS inverter is using as depletion mode MOSFET as the load device and enhancement mode transistor as the functionality device, that is pull down device. So pull down transistor is nMOS enhancement and pull up transistor is depletion mode transistor. That depletion mode transistor of the pull up is used for the output to pull from 0 to 1 and pull down transistor is used to pull down the value from 1 to 0. So output is making the 1 with the help of this depletion mode transistor and output is 0 with the help of this enhancement mode transistor. And in the pull up device for the enhancement, in the pull up device for the depletion mode transistor, VGS is connected as 0. In this mode that depletion transistor is switched on, so we are using at this condition. And this depletion mode transistor inverter is equivalent to resistive load transistor or resistive load inverter. So this depletion mode is exactly equal to the resistive load since this depletion mode is always in the on condition. And the output is taken from the drain of the nMOS enhancement transistor and source of the nMOS depletion transistor. And input is connected at the gate of the nMOS enhancement transistor. So by seeing all these constructional features, if we construct a circuit that will be look like this. That is nMOS enhancement transistor, nMOS depletion transistor as a pull up. This is called pull up and this is pull down device and this is the gate, this is the source. So VGS is equal to 0 here and input is applied at the gate of the pull down transistor. Output is taking from the source and the drain connection of these two and here it is connected to the source. This is the construction of the nMOS inverter circuit. Let's check its operation part by applying the input to 0 and input 1. So when Vin is equal to applied 0, what will happen? The T1 nMOS transistor. So when Vin is equal to 0, T1 transistor is off. Since VGS is equal to 0, it is less than of VT of this enhancement transistor. And T2 is depletion mode and it is always on since VGS is 0 mode. So T2 is always on. Then Since it is always on and it is off now, because of the pull down of output is pulling to the higher value, that is equal to VDD value. Since Vin is less than Vt, this T1 is off and VGS is 0, pull up is on, therefore Vout is pulling to the VDD, and because of open and the pull down, the current is 0 in this circuit, so output is equal to VDD. There is no drop in the output, therefore output is equal to VDD. Then Vin is equal to VDD, that means for logic high what will happen? When Vin is equal to VDD, it is greater than of Vt, therefore T1 transistor is on condition. So T1 is on and T2 is on always. So because of on, here we have a short connection, so therefore V0 is dropping, but here it is not reached to the full 0 value. There is a non-zero output here because of the drop across this transistor. So it is approximately equal to 0, not fully equal to 0 value. That means when Vin is equal to logic 0, the output is equal to the VDD, and when Vin is equal to logic 1, it is equal to the approximately logic 0. And if these two are represented as a characteristic, then its characteristics will be look like this. Vin versus Vout, Vout on the y-axis and Vin on the x-axis, and here output is non-zero for the logic high input and output is full VDD for the logic 0 input. So full swing for the logic 1 output and non-full swing for the logic 0 output. These are the transfer characteristics based on the operation of Vin 0 and VDD application. And we can get these transfer characteristics, that means other than these 2 points of values, what about the characteristics of this nMOS inverter? So we can find the transfer characteristics by using this load line characteristics. What will happen here is, we are taking nMOS pull down characteristics. So nMOS pull down transistor characteristics are nMOS enhancement characteristics. That means, let us see here. Here pull down transistor is enhancement. So its characteristics are like this. For the IDS versus VDS for different values of VGS. But whereas nMOS depletion transistor, since VGS is taken as 0 here, it is having of one characteristic, that is only one. So it is IDS versus VDS for, IDS versus VDS for VGS is equal to 0 value. Now taking of this current and this current, these two current characteristics and overlapping over the one another, then we will find the transfer characteristics. So overlapping of these two characteristics is represented like this. So these characteristics are enhancement transistor characteristics and only one characteristic is used, depletion transistor characteristic with VGS is equal to 0. Now overlapping of these two characteristics will give some points. Those are intersecting points of the I points. So this is the intersecting point, like that we are going to have intersecting points. Now let us check at exactly what value of inputs these intersecting points are coming. So on the x-axis we are going to get VDS, that means Vout value, and this particular intersecting point VGS will be the input value. Therefore, so actually this is VGS is equal to VDD. VDD is the input value and whereas for that output is equal to low value. If you have drawn the characteristic, when the input is equal to VDD, output is equal to 0 value, approximately equal to. So that is, it is representing output is equal to 0 for the input of VDD. And it is not exactly 0, it is some approximately equal to 0, that is represented. And when Vin is equal to 0 value, Vin is equal to 0 value means what? VGS is equal to 0 value. So at VGS is equal to 0 value, the nMOS enhancement characteristic is this, and from this depletion characteristic is this. So intersecting point is this. This intersecting point is representing Vout as VDD. Therefore, output starts from VDD. In middle, if we have taken input of some 0.6 VDD, 0.6 VDD input value, intermediate value of 0.6 VDD, 0.6 value of VGS graph and VDS graph, and then output is equal to this much value. For the input of 0.6 VDD, output is equal to this. That means for the 0.5 VDD, 0.6 VDD means this much. So for the 0.6 VDD of input, the output value is this much. So like this, by having intersecting points of load line characteristics of both pull down and pull up transistors, we can derive the transfer characteristics. So for this nMOS depletion mode pull up inverter, this is the transfer characteristics from this load line characteristics. So this is the transfer characteristics of nMOS depletion mode pull up inverter. Now this transfer characteristics can be varied. These transfer characteristics can be varied. Now let us see how it can be varied. So by varying the transfer characteristics, these are represented here with the three variations in the transfer characteristics. In the three cases, output 0 is non-zero. Here output is not is equal to 0. But in these three cases, for the output, logic high is full high. And here, these characteristics are moving above the Vin and below the V invert when compared to the equal. That is due to the changing of ZPU by ZPD ratios, where here Z is representing as impedance and that Z is representing as L by W value, length of the transistor by the width of the transistor. That means length of the gate by the width of the gate, or length of the channel by the width of the channel. So by using this ratio means when ZPU is representing means ZPU is equal to LPU by WPU and ZPD is representing means LPD by WPD value. Means size of the pull down transistor, size of the pull up transistor. These are nothing but sizes. So by changing the size of the pull up and pull down transistors, these characteristics can be varied. So let us take the middle graph is representing ZPU is equal to ZPD, means both the transistors are having the same size. If ZPU by ZPD is decreasing means ZPD is larger than the ZPU. So ZPD is greater than the ZPU, means pull down transistor is greater than of pull up transistor size. Then characteristic is moving outer side. And when ZPU by ZPD is increasing means ZPU is greater than of ZPD. That means when pull up device is stronger when compared to the pull down device, the characteristic is moving this side. Here V invert is a point where V input and V output both are same. So V in is equal to V out is called as V invert here. That will be represented over the graph. So this is equal to V invert for the first when ZPU is equal to ZPD sizes. Then this V invert is increasing, this V invert is decreasing in the V invert is representing as V in is equal to V out. This V invert is increasing when ZPU by ZPD is decreasing, and this is decreasing, V invert is decreasing when ZPU by ZPD is increasing. So like this V inverting point can be shifted so that asymmetric characteristics can also be achieved. When both are equal, this is called the symmetric characteristic. When asymmetric characteristics means the duration for the logic high and logic low are not equal. So depending upon our application, if you want, we can achieve both symmetric and asymmetric characteristics by changing the ZPU by ZPD. But normally symmetric characteristics are required when we are considering in the logic gates and logic applications. Therefore, the sizes have to be taken care of the transistors to maintain the symmetric characteristics. Let us see its static behavior. That is, power dissipation is high since there is rail to rail connection always when Vin is equal to logic high. That means in the circuit, since load device is always in the on condition and this down device is on for input is equal to logic high. So both are on means there is a short connection between the two power rails. Therefore, power dissipation is high. Then output is full logic high for the output of 1, but output is non-full logic 0. So 0 is non-full, but 1 is full. That is representing in the characteristic also. And in the circuits, whenever two transistors are connecting in a cascade with the direct connection or with the help of some pass transistors in between, the sizing need to be taken care to maintain the V invert point and delays and as well as output voltages. So here two cases are representing. One case is inverter is directly driving the other inverter and inverter is driving the other inverter with the pass transistors in middle. The sizes here required are ZPU by ZPD ratio of the second inverter should be greater than or equal to 4 by 1 when compared to the first inverter. For this case, for sending the original signal as it is without any loss, without delay or with less delay and symmetric characteristic. Here also to get the symmetric characteristic and less delay and less loss, if inverters are connected with the pass transistors in middle, the size should be for the second inverter when compared to the first inverter it should be more and its size should be greater than or equal to 8 by 1. That means in this pull up and pull down two transistors will be there. Let us take pull down size is 1:1 and pull up is also 4:1. In the second case we have to take as 4:1. Similarly here 1:1 and 1:1, it should be 8:1 and 1:1. So the load device should be of that much size. So therefore it will pass all the signals as it is without any delay, without any change in the characteristics. Let us see this quiz. For the depletion mode transistor, gate should be connected to. We have seen this is nMOS inverter with its gate connected to the, this is the gate, this is the source, gate connected to the source and which are connected to the out. Therefore, gate is connected to the source. Then in depletion mode pull up, dissipation is high. Yes, dissipation is high since current flows when dissipation is high or when current flows, when the pull down is on, since the static path is existing between two rails, therefore current is high. When Vn is equal to 1, this transistor is on. So Vn is equal to 1 case. In inverter circuit, dash transistor is used as the load. In this nMOS inverter circuit, nMOS depletion mode is used. Or in the nMOS inverters, we can use enhancement, depletion and etc. So therefore, we can use anything. Then an inverter driven through one or more pass transistors has ZPU by ZPD ratio of through pass transistors means its value should be equal to 8 by 1 or greater than 8 by 1. Let's take these questions as assignment questions and solve these. Describe the transfer characteristics of nMOS inverter and derive ZPU by ZPD ratios for the two cases which we have discussed as values of 4 by 1 and 8 by 1. So derive ZPU by ZPD when two inverters are directly cascaded and two inverters are cascaded in middle with the help of the pass transistors. Follow this textbook for this topic, that is Pucknell Essentials of VLSI Circuits and Systems. What we have seen till now? We have seen nMOS inverter circuit, its operation, its static behavior, its transfer characteristics, and finally the ZPU by ZPD ratios, that is sizing of the inverter when it is used in the cascading issues. I hope you have understood this nMOS inverter. We will see CMOS inverter in the next lecture. Thank you.